Mm-hmm.
Okay, so today with this experiment, we're going to look at a surface recording of an earthworm action potential. So in this case, we don't have to like plug electrodes into an axon of a giant squid or anything. The signal is so powerful you can actually get a facsimile of it just by putting electrodes on the surface. So we have our earthworm that's laid out here anesthetized with alcohol. And we have some stimulating electrodes here that are going to stimulate the medial axon, which runs down the ventral surface of the worm. And we have a ground electrode and some recording electrodes. And so one of the things we'll do today is we'll look at this time it takes to get an impulse from here to here. So that'll give us some idea of conduction speed, and we'll compare that to the human that you did earlier. We'll get an idea of threshold, so there'll be a voltage stimulus here, at which point we'll get an action potential response trigger. And we'll talk a little bit about refractory periods, so the amount of time that you need between stimulation in order to get to successive action potentials. So your setup is already going to be ready for you when you come to class. You have the worm out there, and you have the stimulator panel. And what we're going to mess with first is the voltage. So we're going to start at 0.2 volts, and we're going to hit start. See, we might want to click that and start over. Experiment we want to do, we want to find out the threshold, so the stimulus that it takes to initiate an action potential. So if we start at a low voltage, and here we're just going to start at like, I don't know, 0.3, and we hit start. This is the stimulus peak, and there's not much in the way of a signal. Let's do it one more time to see if that flattens out a little bit. Flattens out a little bit. Let's go up to 0.4. Let's see what we get. There, you're starting to see a peak here. Let's go back down to 0.35. Hard to say. Let's go back down to 0.3. So everything's pretty flat, even though it's kind of curvy. A little bit high background. 0.35. The worm is moving around a little bit. Kind of hard to tell there. Let's go to 0.4. Do a couple of recordings. This is kind of looking like it's it. The worm is moving a little bit, so that's why we're getting background. But anyway, this is probably that's the action potential. You go up a couple of steps, 0.45, get the same peak here, but it's, just do one more for good measure there. Let's go to 0.5. Same thing. 0.6. Same thing. So this is the stimulus peak. Notice that gets bigger at each step, but this one does not. And you can do the measurements if you want. Now, while we have them here, we can grab our M. So notice that the time scale on the bottom there is milliseconds. So if we take M, and we put it, I don't know, at the top of the stimulus peak here, and then we put our cursor on the peak of the action potential, you get, what's that, 5.575 or 5.6 milliseconds. Write that down on your lab. And then, so that it takes 5.5 or 5.6 milliseconds to get from this stimulating electrode to the middle recording electrode, and that's a distance of 8. Looks like about 8.1 centimeters. So if you divide, use your handy dandy calculator again. 8.1 divided by 5.6 milliseconds equals 1.44 centimeters, 1.45 centimeters per millisecond, which is the same thing as 14.5 meters per second. So compare that to the human that we did before, which was about 45. Okay? Now what we're going to do, since we have a pretty good signal on this one, get rid of our M, we'll change the frequency. And so it'd be nice if you could do this simply, but if you change the frequency to 0.7, you get this little table which is in your lab actually. Change the frequency here. This becomes the interval between pulses. So I just put in 66.7, so that gives you 15 milliseconds between pulses. And if you hit start, you see the action potential, probably here and here. You see the second stimulus peak, and then the other action potential would be over here. So that's the first action potential. This is the second action potential. We'll do one more at this one just to make it a little clearer. So there's the first action potential. You can't really see the second one is this one. All right, now let's change. So that's at 15 milliseconds. Let's go down to, I don't know, 8 milliseconds in between. So we'd have to change the frequency to 125. And we hit start. And let's just get a second one here. So we got the action potential here. You get the second stimulus, or the first stimulus pulse, and the action potential is going to be out here. Second action potential is going to be here. Here's the second stimulus pulse. Okay, so let's do one more just to clean that up a little bit. Here's the action potential right here, here. One more. So here and here. Looks like we're recruiting, with the first one you're recruiting the other axon that's running down the middle there, and that's why you're seeing 2 peaks here. We've hit the refractory period on one, but not on the other. So you're seeing this peak here with this one. Now let's go up, we're at 8, so let's go to 6. So we change this, what was that number again?
166.7.
166.7, somebody's paying attention. Oops. Somebody's paying attention here. And there you can see maybe, let's do it one more time. You see a little hint of that first, or that second action potential right there, but it's kind of covered up by the stimulus peak. Here's the other one, the first one. So let's see if that little hump there goes away. If we go a little bit further, so to 5 milliseconds. Start. There. You have the action potential here. Let's do one more. You have the action potential here. You have the 2 stimulus peaks, but so you can stimulate with the first stimulation, you stimulate action potential, but it's too soon. The second peak, the second stimulus comes in too soon to stimulate the second one. And that's 5 seconds, so that's what you get for the refractory period. Okay? So pretty cool. Refractory period, threshold, and conduction speed are the 3 things we wanted to get from this. And then you can compare that to the human, and then there's a number of questions for you to answer in the lab. That's it.